We'll continue with our study of advanced inflow models. So far we have looked at the Coleman's model, which is you take one single vortex, which is a helical structure, distorted structure, break it, think of it as a spring, break it, and then each ring of a circular part of a spring, squash it into a circle. So you get a nice closed circle. So this looks like the way it is in the top view. This is the side view. We said Coleman numerically integrated over each circle, assuming some vortex circulation strength, which is an average, azimuthally average circulation strength, which could come from what we call a Kutta-Joukowski theorem. Remember, L prime equal to rho velocity times capital gamma. So gamma is the circulation. So you take the peak circulation and use some fraction of it or some modified version of it. So he did this work. This is Coleman's model. We talked about the Dries model. We talked about the Blake and White model. Then we talked about the Castle's model. Castle's modeled it as instead of a discrete rings, as a distributed sheet. Castle's was able to analytically integrate it, and he tabulated it, made a graph of it, so engineers don't have to go through the grunt work of doing all the integration and calculations. Later on, Hayson came, and he said instead of just one sheet like this that he has at the tip, I'm going to have a multiple vortices shed all over the rotor. Each one produces its own vortex sheet, like a skewed cylinder. I'm going to analytically integrate over it. So this was the Hayson's model. So now we are going to go to slightly more advanced models. So around 1965, computers became available, digital computers. So engineers modeled the tip vortex initially as a rigid helical structure. Then they started distorting it, modifying it, and they also allowed the strength of the tip vortex not to be constant everywhere like the previous models did. They allowed it to vary once the vortex is released, it holds its strength. But as the blade is going round and round, it's constantly releasing vortices, tip vortex structures, so the strength can vary azimuthally. Okay? So the induced gamma can vary azimuthally. So they had to use a Biot-Savart law numerical integration to compute the induced velocity. So people like Sadler at Bell Helicopter, Scully at MIT, his classmate, college mate at MIT was Wayne Johnson. They used a numerical integration. Assume a wave shape, distort it, if necessary, if possible. Then for each, break the tip vortex into small straight line segments, compute the induced velocity from that straight line segment using Biot-Savart law, sum up over all such straight line segments, then you get the induced velocity at the rotor disk. By the way, you can also compute the induced velocity on the wake itself, self-induced velocity. Then that filament then starts moving at a slightly different velocity. It does not move up and down at the Glovertian flow velocity. It does not move left to right, just at the free stream velocity. Because of the self-induced velocity, you have a slightly different value. So now the wake starts deforming, distorting. So it's a computationally intensive effort, but with digital computers, this can be done fairly quickly. We are talking about the after order of a few minutes. So perhaps seconds nowadays with the modern supercomputers. So programs such as Camrad, ArcAS, Dymore, UMARC, Host, other programs use either a rigid wake or a distorted wake or a free wake. So this is an example of a wake in the aerofoil generated by an aerofoil as it pitches up and down. Notice that the wake structure is not a flat horizontal line like the way our skewed wake model will do. Everything does not blow linearly left to right. Plus it's distorted. It's rolling up into strong structures. So this needs to be captured. So this type of a wake you see in this direction, in this view, is called a shed wake. This is a span-wise or a radially wise wake structure. This is called a shed wake. Whereas the wake structures we have been talking about until now is called a trailing wake. So a helicopter, because of its unsteady nature of the environment, can shed wake in the wake structure. It can also shed wake in the trailing direction. So in reality, therefore you get both the shed wake structures, which are shown as a red line here, and trailing wake structures shown in the blue line here. And the tip vortex is also a trailing wake structure. It will have the strongest strength. So in some computer programs, they will neglect everything except the tip vortex. In other computer programs, they will say, I'm going to keep the first 90 degrees of the shed wake. After that, I'm going to neglect the shed wake and the inboard vortex, the trailing vortices. After 90 degrees or 180 degrees, I'm going to keep only the tip vortex structure in play. So blade is divided into a number of radial directions, and each radial location, in the middle of the strip, you shed a wake, a vortex, because at the junction of the two blade elements, you shed a wake. Left, convert that into from Biot-Savart law, not Biot-Savart law, using Kutta-Joukowsky theorem into circulation. Then whenever the circulation jumps, you have a trailing wake. Whenever the circulation varies azimuthally, you have a shed wake. So, for example, if you have one element has got a circulation of gamma, the next element has got a circulation of gamma plus delta gamma, then you shed delta gamma. So if the strength is increasing as you go from left to right, you feed circulation. That means our arrow vector is pointing upwards. On the other hand, if gamma plus delta gamma is less than gamma, then you are removing circulation. That means the vortex is going from top to bottom in this picture. Right-hand screw rule applies to the orientation of the vortex. So that means if the vortex is pointing upwards, think of it as a screwdriver that's pointing, its tip is pointing upwards. So you turn the clock and the screw in the clockwise direction. If the vector is pointing left to right, as in the shown along the blade, think of it as a blade tip, it's a screw tip of a screwdriver. Then you turn the screw in the clockwise direction. Okay, so right-hand screw rule. How about the shed vortices? So one azimuth location psi, another location psi plus delta psi. If the strength gamma changes, then the delta gamma at a given blade element in the azimuthal direction gets dumped into the wake, just like this aerofoil was doing, vortices in the wake. Okay. So you have shed vortices and you have trailing vortices. So calculations are done in a time-marching manner. There's lots of nuances. I have some papers by Wayne Johnson. We have some PhD dissertations from University of Maryland, from Professor Leishman's students. My own students at Georgia Tech, in a program called GT Hybrid, we compute the induced velocity. There's lots of information available. So you either use with a helical wake, rigid wake, or a prescribed wake, that means it's a helical structure with a prescribed geometry, or a free wake which is allowed to distort, deform. So 3 levels of sophistication are available. Comprehensive programs will have all these options available to you. You can turn them on or off. So how does the rigid wake look like? It is like this. So the x location is in the lateral direction. The wind is blowing from left to right. Mu x and mu z or the total inflow, if you will. Okay, pardon me, the free stream velocity, if you will. And then x is defined this way. So if the free stream may be going from left to right, it may be going from top to bottom. Okay. So when it may be also blowing laterally. So not only the x may change, but also in the y direction you may have things changing. In the z direction, you have a downward directed induced velocity plus a free stream velocity, Glovert inflow. If you only use a Glovert inflow, you get a constant downward lambda, then you get a nice rigid helical structure. So this is the rigid wake model. Now the wake age is called a phi. That's what is showing up here. It's the time between when it is where the blade is and where the vortex is. Okay. So vortex is released, then the blade has moved past it. So if the tip vortex is released at a point that's shown as a circular blue dot here, If the blade is at a different location at a phi, then phi is the wake where the blade is. Okay. This is the thing. Psi is any location downstream of when the tip vortex was released. Okay. So psi is, let's say you have any point on the purple line below this blue circular dot. So that corresponds to the different azimuthal location psi. So psi minus phi is called the vortex wake edge. So when you first release it, it's got a wake edge of 0. Blade has moved past it, then the wake is left there. It starts descending downwards. So previously released vortices are older than the currently released V at phi. So when psi equal to phi, you get a 0 vortex edge. When psi is greater than phi, you have older wake structures. So you get lots of wake. So this is the rigid wake structure. So this is one of the models that will be available in many computer programs. The next sophistication is so-called a prescribed wake model, just like the Robin Gray used to do. The most common prescribed wake model is from Alan Egolf and Jack Landgrebe. Alan used to work at Sikorsky Aircraft. Then he went to United Technology Research Center, Jack Landgrebe there. Then Alan came back towards the last few years of his wonderful career to work at Sikorsky. He was a mentor for many of the engineers at Sikorsky and also for my own students. So basically, the Z vertical descent is given as an empirical function like this. E and F have got a lot of empirical constants. And G is a Fourier series. So it's got lots of constants, C0, C1, C2, C3, Cn, D1, D2, D3, Zn, Dn. These were curve fitted from the experimental data observations by Alan Egolf and Jack Landgrebe. So you could use a wake structure like this. Now it will be distorted, at least in the Z direction, the wake will have a non-uniform variation azimuthally. It won't be a nice helical ring like a spring-like structure. A spring that is, you have stretched it and moved it sideways. Okay, then you have a helical rigid structure, which is what this is. The stretching rate is dependent on the Glovert inflow velocity and the induced inflow plus free-stream velocity, capital lambda. Here is the lambda I plus some extra stuff. Okay. So this is a prescribed wake model. Finally, if you use a self-induced velocity, Biot-Savart law, use that velocity to advance the flow from one location to the other. Velocity times delta t is the distance that particular vortex filament will travel. Then you get a highly distorted structure. This is a free wake geometry that was computed by Professor Gordon Leishman. Used to be at University of Maryland. Now he is in Embry-Riddle in Florida. And this is from our own GT hybrid, Georgia Tech, for a coaxial rotor. Basically, they start like a nice rigid wake structures, but as they move from left to right, because the helicopter is moving forward away from its wake, the self-induced velocity causes significant distortion. Filaments come into close proximity from each other and so forth. The methodology that we have described is given by Wayne Johnson. It is in his most recent program called Camera 2. So the website has got some papers by Wayne Johnson, by other people. Everything we have proposed, described here, is available. So we have concluded the inflow models. Very good thumbnail sketch. So we will stop this particular video at this point.